favorite stuff. All right. This is the IB version of Snell's law here, right? So if we've got, let's draw a picture. We have air here, and we have glass. Okay, and we've got a line perpendicular here, right? If a laser light comes in like this, it's going to bend like this because it's slowing down, and the right side of this wave train slows down first. So it's a bit like putting the brakes on the right side of your car. Okay. Incidentally, those calculus problems where the lifeguard can run so fast on the beach and swim only so fast, right? They follow the same path dictated by this, which is one of the coolest things, right? Okay. And so this is let's say this is theta 1, and this is n1 and the velocity 1, right? So remember that n is, what is n? N is velocity, the speed of light over the velocity, right? So indices of refraction are bigger than 1 because the velocity is in something besides a vacuum, right? I think this is glass, right? You can see those velocities are smaller, right? Okay. And so we're dividing the speed of light by a number smaller than the speed of light, and we get a number bigger than 1. Right, so n really is a measure of how much it slows down. Remember that. And here we've got n2 and we've got v2, right? And v2 is slower than v1. n1 though n2 is bigger than n1, right? v1 is bigger than v2. Anyway, I don't know. We'll figure this out. Okay, and then this is our theta 2 here. So notice that these angles are measured not with the surface, but they're measured with perpendicular, like this. Okay. So we draw a line perpendicular. Don't know why we did that, but that's what we did. Okay, so we've got that. That's the most convenient thing. This is Snell's law. Really, it's usually written this way, n1 sine theta 1. If I cross multiply this first equality there, equals n2 sine theta 2. Right? Okay. If I cross multiply this one, I get something different, right? And you can mess like that, but that's what it is, right? You can calculate that given the index of refraction. So air is roughly, n is roughly 1.003 or something like that, right? I think water is like 1.34 or something like that. Or sorry, glass. I don't know. Glass could be more, right? I don't even know. Okay, but it'll bend like that, and that's what this guy's for. Okay. And then these guys are the interference things, right? So if I've got a speaker here and a speaker here, and these are the same frequency, right? The same phase, right? So remember the position of something is x naught times sine omega t plus phi. In the simple harmonic motion thing, these speakers are moving in and out with this thing, and both speakers have the same phi, right? Right? They have the same omega. By the way, the same phi is not critical. Same omega is absolutely critical for this to work, okay? And so if we pick a spot here, and the question is, what are we going to hear? Well, it could be constructive or it could be destructive, right? And so if we measure this is I'll call this speaker 1. Speaker 2, I'll call this the length 1, and the length to this speaker is slightly different, right? Length 2 looks shorter than length 1, right? Okay, so if I figure out L1 minus L2, and this is the absolute value of that, that's the path difference. And if it's an even number, these are integers, right? 1, 2, 0, 1, 2, 3, etc., right? If it's an even number, then you will have crest meeting crest, and it will be constructive and it will be loud. Or if it's light, it will be bright. Or if it's an earthquake wave, look out! Anyway, I don't know. All right, so that's what they're talking about, right? If it's destructive interference, then you have a half wavelength difference in distance, right? Okay, and when you have a half wavelength difference, right, a whole wavelength looks like this. Right? A half wavelength separates a crest and a trough. So if you have a half wavelength difference, you get destructive interference. So those noise canceling headphones you have, they're clever. They hear the sound coming in, and then they just create a wave that's a half wavelength off, and you get destructive interference, and it cancels the sound is really kind of cool. And I think we did this last year, right? We played the same tone in these speakers. We walked around, we could hear loud, soft, loud, soft, loud, soft. And in that case, it wasn't just the sound coming from these speakers, but it was also the reflection. So it was probably massively complex, right? Okay. So that's this part. Okay. Now we're getting into like Young's double slit, right? And diffraction problems, right? So this is Young's double slit experiment, right? So we have a barrier and we have a slits there separated by a distance d, right? We are separated from a screen that is some distance away. How far away is it? It's big D away, right? Okay, then we have light. Let's change the color here. Oh, gotta wait for it. Okay, we have light coming in. Maybe it's a laser beam, and it's monochromatic, and it's coherent. Okay, so this light is coming in like this, right? And what's going to happen here is it's going to spread out, and these two slits are going to act like two different speakers. It's going to diffract away from here, and on the screen, you're going to get a bright spot, dark spot, bright spot, dark spot, right? These little bright spot, dark spots, right? Okay, and these little bright spots, dark spots are separated by a distance s, and that's what this formula is about, right? So we've got a wavelength of light, that's this guy, right? We've got the distance to the screen, that's this guy. This is the small distance, right, separating these little slits, right? And then this is the distance that separates these little bright spots, right? That's S right there. And, they're all supposed to be evenly spaced. Of course, that's impossible because this, anyway, don't think about it too much, right? And these are, I've drawn it here where these angles are really quite large, like 30 degrees. But we're talking about, like I'll set my laser up on the front counter, and on the wall, probably 8 meters away, these dots are just like, they're literally like bright spot, bright spot, bright spot, like that, right? They get fainter as you go out, right? So literally they look like this. If we go all the way across that giant room, the physics room, they're really small. So these angles really, really are very, very small. This is an approximate formula. Okay. This is the actual formula, right? This is what you're supposed to do. This is what you want to do. It's kind of like the food pyramid. This is what you're supposed to eat. It's got all that stuff in there, right? This is what you want. This is potato chips, All right. So this is the exact formula, right? So if you wanted to figure out these spaces exactly, you could do this and do all the trigonometry involved with finding that angle, the inverse sine, and then tangent and all this stuff, right? And you'll get exactly these numbers, right? Unless you have a special circumstance, okay? So that's the Young's double slit. This is the single slit pattern. And I don't know, in retrospect, I gave immensely complicated single slit patterns. I've never seen hard ones on the tests, right? But a single slit can generate an interference pattern. I got to draw it the other way. I have to draw it coming down, right? Okay. We got to draw, we got a slit here, right? And it's got a width of B. We've got light that's got a wavelength of lambda coming down, right? And the angle, and what we get is this pattern. It looks like this. So there's a central bright spot. And then it goes, oh, this is terrible. Let's see if I can do this side better. Whoa. Okay. And technically, we're supposed to say the sine of this is that, right? But we don't do that because for small angles, you can try this in radians. Put your calculator in radians, right? The angle equals the sine of the angle for small angles. Right? And that's because, of course, if we look at the origin here, right? The sine, if you zoom way in on it, it's just y equals x, right? It's the slope of 1 at the origin, right? So it works, right? For small angles. And we're only dealing with small angles, so there it is, right? But anyway, if we look at this, we've got this single slit, and we've got this interference pattern. So I'm going to draw it better. This is intensity is my vertical scale here, right? goes. It doesn't make that sound though. Okay, this distance here is lambda over b. This is 2 lambda over b. If it was to here, it would be 1.5 lambda over b, right? Right? Is the angle separation. Really, that's sine angle. But they're just saying it's the angle, of course, in radians, right? So just don't forget that as a single slit diffraction pattern, it's got a central bright spot. And yeah, and telescopes, by the way, refract because they're just a single hole. And the refraction of telescopes actually limits their ability to pick up angles, which is interesting. Yeah, the resolution of telescopes depends on their diameter. Also, their light gathering ability. I don't think I need to say anything more.